Hello, and welcome to the session on permutation and combination. In this particular video, we'll talk about arrangement and selection. To begin with, or to continue from my previous video, in how many ways can you arrange 5 children on 5 seats? If you remember, we had discussed n things on n positions can be arranged in n factorial ways. If you want to look at it again, the logic behind is on the first seat, any of the 5 children can come. On the second seat, any of the remaining 4. On the next seat, any of the remaining 3 children can come. On the next seat, any of the remaining 2. And on the last seat, there is just one child who is left and he can come there. Now, what happens if instead of the children and number of seats being equal, it is different? That is, you have to arrange 7 children on 5 seats as it is shown here. In that particular case, on the first seat, how many children are possible? Any of the 7 kids can come there. Then on the second seat, any of the remaining 6. Then on the next one, any of the remaining 5. On seat number 4, there are 4 kids remaining. And for the final seat, there are 3 kids who are still left. So those 3 kids can come there and 2 children will have to be seatless or will have to go back. So this comes out as 7 into 6 into 5 into 4 into 3. Now instead of writing it like this, what I can do is I can multiply it with 2 into 1 and also divide it by 2 into 1. Why am I doing it like this? Because if I do this, the entire thing in the numerator, what I have is 7 factorial and what I have in the denominator is 2 factorial. If you notice, this is nothing else but 7 factorial by 7 minus 5 factorial. Why am I putting it in this complicated way? Well, you will understand that once we move on to the next question, which is in how many ways can you arrange n children in R seats? Now, for the first seat, how many choices do you have? For the first seat, you have n kids. For the second seat, you have n minus 1 kids. For the third seat, you have n minus 2 kids. For the fourth seat, you have n minus 3 kids. If you notice the pattern, for the first one, n kids, second seat, n minus 1 kids, third seat, n minus 2 kids. Let's say for the 20th seat, how many kids will be there? N minus 19. It is all one lesser. So, for the final seat, which is actually going to be the rth seat, how many kids are going to be left out or how many kids are going to remain? That will be n minus r plus 1, which is something that you can observe from the pattern here. Now, once you have identified this, this is the value, this is the answer. But as you can see, this is a little hard to remember. To avoid this hardness to remember, people came up with a formula. And for coming that formula, what they did was they multiplied the numerator with a certain amount of values, that is n minus r minus 1, and went on till 3 into 2 into 1. Why did they multiply it with this set of values? Well, you guessed it right. They multiplied it with this set of values to get n factorial in the numerator. But if you are multiplying with a certain value in the numerator so that the value does not change, you also need to multiply with the same value in the denominator. Once you have done that, what do you get? In the numerator, which is given here 1, 2, 3 till n minus r is what we multiplied with, and you had n minus r plus 1 till n. So you got an n factorial in the numerator. And what did you get in the denominator? N minus r minus 1 and so on, which is nothing else but n minus r factorial. So this is essentially the value that you got, and this is nothing else but NPR. And that is how we get the formula for NPR as n factorial by n minus r factorial. So once again, when can you use NPR? When can you use this particular formula? This particular formula can be used when you have to select R things from n distinct, when you have to select R items from n distinct items and arrange them. See here, you were arranging the children on the seats. Isn't that? So, whenever from n things you have to select and arrange r things, you will use NPR or the formula n factorial by n minus r factorial. To continue with this idea and a few other similar ideas, let us look at a few more questions. How many words can be formed by rearranging the letters of Nokia? Well, it's very simple. 5 letters, they can be rearranged in 5 factorial ways. Is the next question the same? Are Nokia and Apple the same? Well, as brands they are not, they are very different, and even in terms of letters, they are very different. 5 letters Apple, but it can be arranged in 5 factorial ways, but that is incorrect. You need to divide it by another 2 factorial. Why do you need to do that? Because the two p's are identical to each other. So what if the two p's are identical to each other? How does dividing by 2 factorial solve the problem? It solves the problem because if these two letters were distinct, then you would have been able to arrange those two p's among themselves, which is not possible now, and that is the reason you need to divide it by 2 factorial. To look at it even further, let us look at the word management. In how many words can be formed by rearranging the letters of management? So first of all, I need to identify how many letters does this have. So this has MANA 4, 5, 6, 7, 8, 9, 10. Management has 10 letters. So it can be arranged in 10 factorial ways, but there are some repeats. A is repeating how many times? 1 and 2 times. So A is repeating 2 times. To take care of that, I need to divide it by 2 factorial. M, is that also repeating? Yes. M is also repeating twice. So I need to again divide it by 2 factorial for the 2 M's. N is also repeating. So I need to divide it by 2 factorial for the 2 N's. What else is repeating? E is also repeating twice. So I need to divide it by another 2 factorial. What else is repeating? Well, I don't think there is anything else repeating. There is G which is not repeating and there is T which is not repeating. So, the number of words that can be formed by rearranging the letters is 10 factorial because you had a total of 10 letters divided by 2 factorial for the 2 A's, 2 factorial for the 2 identical M's, 2 factorial for the 2 identical N's and 2 factorial for the 2 identical E's. So that is your final answer for rearrangement of letters of management. Let us look at another very similar question which is based on this particular concept and it has been asked also previously in exams. Let's say you are at point A and you have to go to point B taking the shortest path. Then there are how many ways to go from A to B? Well, one way is you can go till here and then turn right, or you can first go right and then go up, or let's say you went 2 up, 1 right, 2 up, 1 right, 2 up, 2 right. So there are various ways, but how many are actually there? Well, to identify that, you need to see how many possible choices are there. There are 4 rights that you will need to make and there are 6 ups that you will need to make. See, 1 up, 2 up, 3 up, 4 up, 5 up, 6 up. Now, whatever is the rearrangement of this 4 right and 6 use, that will give you a unique way. How so? Well, this order represents right, 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 up, 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 which is right, 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 up, 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 and you have reached from A to B. Rearrange it any way you like. Let's say R, up, up, R, up, up, R, up, up, R. So in this, what is happening? You went right, then 2 up, then right, then 2 up, then right, then 2 up, and then right, and you have again reached B. So whatever is the number of ways of rearranging this is going to be your answer. And in how many ways can you rearrange this? 10 entities can be rearranged in 10 factorial ways, divided by 4 factorial because the 4 rights are identical, and also divided by another 6 factorial because the 6 u's or the 6 ups are identical to each other. Let us look at another variation of this problem. In this, what has happened is you have to go from A to B, There are 4 rights, there are 6 ups, but there is a special road which has been constructed by merging these roads. Now what is the shortest path? Now for the shortest path, you need to go from A to this particular point, take the bridge, and then from this particular point you need to go to B. Let me call these points P and Q. So your path is now predefined. It has to be A, P, Q, P. Now, in how many ways can you go from A to P? Number of ways of going from A to P. There are 2 rights and 2 ups, which is possible in 4 factorial by 2 factorial ways, which is 24 by 4 or 6 ways. From P to Q, you have to take that particular bridge. There is only one way. And from Q to B, how many ways are there? Well, if this is my point Q and this is my point B, there is 1 right and 2 ups, which can be rearranged in 3 factorial by 2 factorial ways or 3 ways. So your total number of ways is going to be how much? It is going to be 6 into 1 into 3, or this is going to be a total of 18 ways which are possible. Now, let us look at another variation of this same problem, in which what happens is, in how many ways can you go from A to B, given that this particular portion has been blocked out. If you keep that in mind, that this particular portion has been blocked out, then what is the difference that is going to come in? Well, your original number of ways or your total number of ways was this much. Let me just copy that. Your total number of ways was 10 factorial by 4 factorial, 6 factorial. But are all these total ways valid now? No, all these total ways are no longer valid, because it will contain some ways in which this particular road, which is now rubbed off, was used. So, how many are invalid ways out of these? To figure out the invalid ways, we need to figure out how many ways are there. Let's say if this point was P and this point was Q. PQ is the road which has been removed. Now, the invalid ways are those in which you go from A to P, then from P to Q, and then from Q to B. So how many ways are there for that? A to P is 2 right and 3 up. So which is RR, UUU can be rearranged in 5 factorial by 2 factorial, 3 factorial ways. P to Q is still 1 way. And from Q to B, how many ways are there? Q is this point, 1 right and 3 ups. So that is R, UUU, which is 4 factorial by 3 factorial. So out of the total ways which were there originally, how many are invalid? The number of invalid ways, 5 factorial by 2 factorial, 3 factorial is 10. 4 factorial by 3 factorial is 4. So total invalid ways are 10 for A to P into, from P to Q there is 1 choice, and from Q to B there are 4 choices. So there are 40 invalid ways. So what is the valid number of ways, or what is my answer? Total minus 40 is going to be my answer in this particular case. Now let us look at a few other type of arrangements. What happens when you arrange n distinct items in a circle? Well, in a circle, it becomes n minus 1 factorial. Why does it become n minus 1 factorial? Because we need an identifier. For the first person, let's say there are n people going to sit on n chairs which are there in a circle. How many choices does the first person have? Does he have n choices of chairs? No. If you don't agree with me, think of it this way. Let's say you have 5 red t-shirts. In how many ways can you decide which t-shirt to wear? If you think 5, you are wrong. Because there is only one way of wearing a t-shirt. You have to wear a red t-shirt. All your t-shirts are identical. It is not going to make a difference. And that is the case which happens with the first guy. Because when he comes into the room and he sees n chairs arranged in a circle, there is no starting point. There is no ending point. he has to pick any chair randomly out of that lot. So he does not have any choice. However, the second person who comes in, he gets a reference point. He gets the first person as a reference point and he will have n minus choices. Next person will have n minus 2 choices. Next person will have n minus 3 choices and so on and so forth. That is the reason in a circular arrangement of n distinct items, it is n minus 1 factorial. What happens in case if it is a circular arrangement in form of a necklace? Well, n minus 1 factorial happens because of the circle, but there is another divided by 2 part. It is very important to understand why this divided by 2 part is there. Think of it that you are wearing a necklace. What is the difference between a necklace and a circle? The additional facility or the additional feature that a necklace provides is that you can take the necklace out, flip it and wear it again. What I mean by flipping it is, let's say there is you are wearing a necklace, you take out the necklace and then you reverse it or kind of form its mirror image. Then there is another arrangement which you have got. So by making the same necklace, you are taking care of two arrangements. And that is the reason why it is divided by 2. But please keep in mind, this necklace funda of dividing by 2 will work only and only in case of objects which are same from the front and the behind. Let's say beads, it would work. Flowers, it would work. It would not work in a case of, say for example, if you were making a necklace of human heads. That would be weird, I'm not questioning that. But let's say if you were making a necklace of human heads, this idea is not going to work because the human head is not same from the front and the behind, and you will not be able to flip it. Now, for selection of r items out of n items, we know that for selection and arrangement, the total number of ways are n PR, which can be written as selection. So I am trying to find out how much is the selection into arrangement. R things on R positions can be arranged in R factorial ways. NPR I already know is n factorial by n minus R factorial. So what is just selection? If I take this R factorial to the other side, what do I get? I get n factorial divided by R factorial into n minus R factorial in the denominator. And this, if you realize, is nothing else but the formula for NCR. So what does NCR mean? When you have to select R items out of n items, then you do NCR. When you have to select and arrange R items out of n items, then you do NPR. A good example of this would be, let's say from a class of 20 people, you have to select 11 people for a team. You can do that in 20C11 ways. However, if you have to select and arrange them, as in present them a batting order of those 11 people, then it will be 20P11. As a thumb rule, you can remember wherever the order is important, it is NPR. Wherever the order is not important, it is NCR. With this, I would like to wrap up this particular session. I hope you liked it. Please provide feedback via Twitter at my Twitter handle @RaviHanda, or you can also email me on my mail ID, which is ravihanda@gmail.com. Thank you.